Hello everyone, my name is Jim, and today we're going to be reviewing DFMA for rocketry. Let's start with what is DFMA. DFMA is an acronym of Design for Manufacturing and Assembly. It's a series of concepts that you can apply to your designs to make them easier to manufacture or assemble. Just because you can design something in CAD doesn't mean you can make it a reality. It's important to note as we work through this that DFMA is more of an art than a science. It takes practice and a bit of trial and error to get it right. So don't worry if your first few times trying to design something for manufacturing, it doesn't quite turn out how you'd expect. DFMA is really two principal concepts, DFM, or Design for Manufacturing, and DFA, or Design for Assembly, that have been crushed together into one larger concept. Oftentimes, DFM and DFA will actually contradict each other, and it's up to you as the designer to balance the two. Some examples of design for manufacturing are reducing the cycle time, choosing easier to machine materials, using fewer tools, being able to complete the part on a less advanced or expensive machine, having looser tolerances, etc. Design for assembly includes concepts such as using fewer parts, a poka-yoke or one-way assembly, larger and easier to work with fasteners, fewer fasteners overall, etc. Since there's such a difference between the two, we're going to split this lecture into two main parts, the DFM and the DFA. Let's start with DFM. DFM applies to every form of manufacturing for every type of product. Each different product or type of product will have a different set of DFM rules. For instance, the DFM for PCBs is different for the DFM for CNCing metal, is different for the DFM for additive manufacturing and 3D printing plastics. DFM can even vary based on the machine type and the individual capabilities of the machine used. DFM that we use for turning is a lot different than the DFM that we use for milling. And even DFM for turning on an SWI prototrack is going to be a lot different than if you're DFM for turning on a Nakamura. So the first and most important step of DFM is to know what your tools and goals are. We're going to split DFM into DFM for milling and DFM for turning, and we're going to start each section with a review of what milling and turning are, respectively. If you've just recently taken Mechie 104 or you're very familiar with the manufacturing process, you can feel free to skip these videos. Milling is the process of removing material with a rotating tool that creates paths through the stock to create the shape of the final part. It's important to note that in machining terms, routing and milling are different practices, but for the scale and scope that our team works on, both of them have very similar DFM rules. So if you ever need to design something to be machined on a router, just apply the same rules that we're using here for milling. Milling tools always have a circular cross-section since they need to rotate around a central axis to work. There are multiple different types of milling tools that will determine how the final part geometry they cut looks. Unfortunately, unlike turning tools, there is no standard code or identifying mark for milling tools, so it can get a bit confusing if you're jumping between multiple manufacturers and sources as you're trying to acquire tools. The most common tool for milling is the flat end mill. Flat end mills create a sharp right angle between the wall and the base of the cut, and can cut with the bottom or sides of the tool. Ball nose end mills are like a flat end mill, except they come to a 180-degree ball at the base of the end mill. These can be used to create smooth surfaces on all areas of a part, or cut slots that have a curved bottom to reduce stress concentrations. They also tend to be used for very small end mills, since the shape of the rounded ball increases the strength of the tool. Here's an example of a keychain that has a 3D curved surface that was achieved by passing over it with a ball nose end mill thousands of times. Facing mills, also sometimes called shell mills, are very large tools that are used to cut the top of a part flat. They cannot cut any other part except for the top, or what's facing upwards in the machine, and they can't take a very deep cut. They're primarily designed for flattening a piece of material or squaring up a piece of material after it's been rough cut with, say, a bandsaw. Chamfer mills are mills that are used for finishing operations, applying chamfers to the corners of parts. Chamfer mills can only cut a single angle of chamfer defined by the tool geometry, so you'll usually see them at a 30 degree or 60 degree angle, but you can get custom ones for any chamfer angle you need for your project. Corner radius mills are very rarely used, but they are still something important to keep in mind. If you needed to round off the top corner of a part, a corner radius mill can impart a determined radius to that corner. The corner radius mill only works for a single radius per tool, so you usually see them sold in sets with quarter-inch increments between the radii. An engraving tip is a tool that can engrave very light writing or images into the top of a part. It's not made for any sort of material removal, but it is good for putting identifying marks into metal. Tools used in milling are usually either made of carbide or high-speed steel. Carbide tools are more common in this day and age, but a lot of the older machines at RIT run better with high-speed steel. The design of the tool can determine what materials it can cut. For instance, a lot of end mills designed for aluminum might only have 2 flutes, but if you try to cut steel with it, the tool would snap instantly. A tool for aluminum can also usually cut other soft materials like copper, and a tool for hardened steels can also usually cut multiple grades of steel. Try and make material choices that minimize the number of tools required for your operation. Tools are sold in nominal sizes, ranging from usually an 1/8 inch to a 1/2 inch, although larger and smaller are available. They usually increment in 1/8 inch or 1/4 inch values through that scale. Tool length is usually a function of the diameter of the tool. The larger the diameter of the tool, the longer maximum stick out the tool will have. For instance, if I wanted to cut a slot that was an 1/8 inch across but 6 inches deep, I probably won't be able to find a tool that can do that. But if the slot was a 1/2 inch across and 6 inches deep, that's probably more realistic. It's also important to note when you're shopping for tools to use for a project that the length of the tool is not the same as its maximum depth of cut. The machine needs to use some of that tool length to hold on to. Usually it's 1 to 3 times the tool diameter. So with this example here, if I have an 1/8 inch tool that's just under 2 inches long, I can expect to cut a slot or a feature that's at most 1.5 inches deep. The best tools are the ones that have the largest diameter and are as short as possible. These tools are the cheapest, the easiest to work with, and last the longest. So while you're designing, try and make features that can be machined with these styles of tools. We're next going to take a brief look at the anatomy of a mill, just so that you can better understand how it functions when designing tools. Every mill looks very different, and they all function in different ways to achieve the same end goal. We're specifically going to look at the PCNC 1100 from Tormach, since it's the most used CNC here at the RIT campus. The spindle is the main driving force of the mill. It's what rotates the tool, and it defines how fast the machine can run, how much material it can remove for a given amount of time, etc. The end of the spindle is called the spindle nose, and this is where the tool is installed. On the Tormach specifically, the entire spindle and spindle nose assembly moves up and down in the Z-axis. The work table is how you secure your workpiece or stock to the machine. It's also sometimes called the saddle in older or larger machines. On the Tormach, the work table moves in the X and Y axis. On a manual mill, there will be a handle on each axis that you can use to move it. On this Bridgeport, for example, you can move the Y-axis by spinning the handle in the front, and the X-axis by spinning one of the handles on either side of the saddle. There's also the knee, which is a large rotary knob that you can use to raise and lower the entire saddle assembly. On a manual mill, you generally cannot move more than one axis at a time, so if you're designing a part for manual machining, it's important that all faces are either in line with or perpendicular to one of the critical axes, X, Y, or Z. If you have a part that requires curves or arcs, Generally, you need to do it on a CNC mill. I'm also going to touch briefly on fourth axis milling. This is not a technique that you're going to see used very often, but it is an important tool to be aware of. Fourth axis milling allows milling around the surface of a round part. Generally what will happen is the machine will obtain a fourth axis, hence the name, in addition to the X, Y, and Z. This fourth axis allows the part to be rotated, and then the same X, Y, and Z axis can be applied. You could use this to engrave on the side of a round part, machine a flat into a round part, or drill holes at predetermined distances around a round part. So let's review what we just talked about. Different milling tools can be used for different shapes. A shorter and larger diameter tool is always better, and fourth axis machining should be avoided as much as possible, but it is there if you need it. Let's talk about work holding for milling now. Milling work holding needs to secure the stock from moving under cutting forces. Milling work holding is generally weaker than turning work holding since the loads are lower. This gives us a lot more freedom in milling as we hold the part than it would in turning. Some common work holding examples are vices, soft jaws, fixture plates, and chucks. The most common work holding for a mill is the milling vise. The part is clamped between two parallel faces that apply up to 5 tons of pressure. A vise can only work if it has 2 flat parallel faces on the part. For instance, you can grab onto a cube in a milling vise, but you can't grab onto a sphere. Soft jaws are a continuation of a milling vise that allow you to grab onto unique geometry using that clamping force of a milling vise. The faces of the soft jaws are cut with a negative of whatever part you want to hold, so that as it clamps, it applies pressure equally along that non-parallel face. These can also be used to repeatedly locate repeated parts. If you're using a CNC, like with this soft jaw here, you can load the stock blank, hit the go button, it will machine, and then you can just put in another stock blank to run the next part. Soft jaws need to be designed on a per part basis, so only use them if you need to. Fixture plates allow you to bolt down very large parts to the machine directly. They're good for large or awkward sized parts, but they have the drawback that you cannot machine near the fixture clamps. This usually means that you'll have to end up doing multiple setups to get cutting all the way around a large part. If you are milling the top of a round part, a lathe chuck can be used. This allows for repeatable centering of a round part. For example, the features on the top of this combustion chamber can be machined while being held in a chuck around the round of the combustion chamber and nozzle below. This would be a lot easier than trying to clamp it in a vise, which is impossible since it's a cylinder, and allows us to not have to waste material on soft jaws. Work holding is incredibly important because if your part can't be held, it can't be machined. You always need to consider work holding as you're designing your parts. Another important aspect of work holding is multiple setups. Multiple setups allow us to flip, rotate, or otherwise reorient the part in between different operations to access more sides. Relative critical features should always be designed to be completed in one setup. Every time we move, flip, turn, etc. the part, there's a chance that we're introducing inaccuracy. So, for example, you don't want to bore halfway through a cylinder, flip it over, and bore the other half, because there's a chance that those 2 holes you made won't perfectly line up. There might be a small lip, or one might be slightly larger or smaller than the other. Another important thing to consider is that you need a datum between each setup. A datum is a feature that was machined in a previous operation that we can then re-reference the position to help the machine know where it is. Let's take a look at this part, for example. This is a housing for a remove before flight arming switch. How would you make this part? I found that it's best to make this part in 4 operations. The first one is drilling the small holes on the side. This one might seem a bit weird to start with, but it's very important that we start with the drilling. Drills are very susceptible to breaking if they go through something called an interrupted cut. If we were to say, mill out the pocket that goes through these holes first, and then try to drill, there's a chance that the drill would shatter when it hits that open space. Larger drills are less susceptible to this, but it is best to avoid whenever possible. Once those holes were drilled, we then drill the long hole down through the entire length of the part, and then open it up to final diameter with an extra reach long end mill. After that, we can grab onto the bottom of the stock, and using one end mill, machine around the entire perimeter and the inside pocket of this part. The last setup would be to flip and grab on that newly machined surface, using one of the newly machined sides as our datum, and then finish the bottom with a face mill and an engraving bit. So in review, there are multiple forms of work holding for milling. Work holding must be considered when designing a part, and the same rules for multiple setups and turning apply to milling. Let's talk briefly about impossible geometry. There's a lot of geometry that you can design in CAD that cannot actually be replicated using a milling machine. The most famous example of this is square corners. If I wanted a part that had an exact square pocket in it, and I sent it to the machine, this is what I would end up with. As you can see, there are curved edges where there should be sharp corners. Since the tool for milling is round, it can only cut corners as sharp as the radius of the tool. For example, this 3/8 inch tool left 3/16 inch corners in the square hole. But what if you actually need to fit a square part into that hole? You could use a smaller tool, which would increase the machine time but decrease that corner radius. For example, if you drop it all the way down to an 1/8 inch tool, you'll only have a 1/16 inch radius. If that still won't work, the most common solution is to drill out the corners. When you drill out the corner, what you'll do is start by drilling 4 holes where the corner should be, then milling out the rest. What'll happen is when the mill gets to the radius where it should be, it'll just be hitting the open air of the drilled hole. This is the same part as before, but this time I used an 1/8 inch end mill and then I used an 1/8 inch drill to drill out the corners. The soft jaw example from earlier is a good example of drilling out the corners. We needed to be able to hold a square part on this left side of the soft jaw, but we obviously can't cut the square corners. So, as the end mill was making its finishing pass around the outside of that part, I programmed it to also go in and make a small loop in each corner. Another thing to look out for is non-standard bottom radii. If the bottom of a slot does not match up with the radius of a ball nose end mill, it'll require hundreds of cutting passes to finish the surface. And even then, the surface won't look that good. So if you look at this example to the side, an 1/8 inch ball nose end mill is trying to cut a slot that was designed with a 1/2 inch radius at the bottom. It tried its best, but you could see that there are some bumps in the surface and even some material that it couldn't properly remove. Another one to look out for is tapered walls. Tapering the walls of a part in a mill is a very complex operation or requires very expensive tools. In general, what will happen is your part will end up with a stepped look to them. It's best to avoid any tapered parts altogether where possible. In review, there is some impossible geometry that must be avoided in milling. Square corners are impossible and require special machining operations. The bottom radius of a slot should match the radius of a ball nose end mill, and tapered walls are very difficult to achieve and should be avoided where possible. Let's talk about stock selection now. Every metal that ever existed has a machinability rating. Machinability is the rating of how easy it is to cut the material with a standard tool. Milling machinability is different from turning machinability due to the lack of deflection, but we'll cover that later on. For now, all you need to worry about is the machinability rating of the material that you're selecting. Machinability in general is a function of hardness, so the harder a material is, the harder it will be to machine. You have to balance between having an easy to machine material and what's needed for the physical characteristics of your part. While round stock can be used for milling, square stock is more common. We'll talk about round stock later on. Square stock can be bars, plates, or sheets. If you're wondering what the difference between a plate and a sheet is, generally the difference is that a plate is more than an 1/8 inch thick. Other than that, they're identical. Bar stock is sold in nominal lengths and widths, and the depth varies depending on your needs. For example, you can find nominal stock sizes of 2 inch by 2 inch, 2 inch by 2 1/4 inch, 2 inch by 2 1/2 inch, etc. But the entire depth of that piece of bar stock can usually be defined by you down to the fraction of an inch. Like with round bars and most long bars in general, it's cheaper to buy one long bar than multiple short ones. Plates and sheets also come in defined nominal thicknesses. For anything above a 1/16 of an inch, it's increments of 1/8 or 1/16 of an inch. For anything below 1/16, it usually breaks down into gauges, and then it follows the American gauge standard. When you're choosing plate or sheet stock, it's important to consider their X and Y dimensions. Plates are usually sold at nominal sizes for the X and Y, and if you need to buy something off nominal, it may add hundreds of dollars to the cost of the material. Try and buy pre-cut or standard size plates whenever possible. Let's do a quick example of choosing stock. Let's say we need to make 100 of this keychain. It's just over 2 inches tall, a little bit over 1 1/8 across, and under 1/4 inch thick. Each part will be machined independently, so we need one piece of stock that encapsulates each of the 100 keychains. We can't, for example, load a plate into the machine and have it cut out dozens of parts from it. What's the best stock option for cutting something like this? If we were only making a few, the cheapest and easiest solution would be to get a 1/4 inch plate and then use a bandsaw to cut X and Y cuts into the final shape parts. If we need this many though, a bar is going to be easier to work with. What we could do is load the bar into an auto-cutting bandsaw, have it move forward slightly, make a slice 1/4 inch down, move forward, slice 1/4 inch down, etc. A 2 1/8 inch by 1 1/4 inch rectangular bar would give us enough breathing room to work with. But we're going to go for a 2 1/4 by 1 1/4 rectangular bar instead. Since 1/4 inch increments in stock are more common than 1/8 inch increments, they cost a lot less. A larger tool may be required to rough out this part already, so that little bit of extra stock that we're taking off isn't really the end of the world. It's always important once you choose a stock size to think about what would happen if you go up a size or down a size from the supplier. Sometimes you might be surprised. One of the hardest concepts to wrap your head around when it comes to stock pricing is that it's not linear. If I had to buy a 1 inch by 1 inch by 1 inch cube of aluminum versus a 1 inch by 0.2 inch by 5 inch bar of aluminum, the bar would be significantly cheaper even though it's the same amount of material. Stock that is large in one direction and small in the other two is cheaper than stock that is about the same in all directions. This is because of the way that a bar is manufactured. Usually all parts are made in 8 or 12 foot increments. The machinery required to make a 1 inch by 1 inch bar will be more expensive than a 1 inch by 0.2 inch bar, and then the supplier just cuts it down to size. Try to design parts that only need long stock in one direction, or is split into multiple parts where possible. The absolute worst stock shape you can have is a cube. Try to avoid that at all costs. So let's review what we just discussed. Machinability is the rating of how easy a material is to machine. You don't really have to worry about deflection in milling. Plate, sheet, and bar stock are most common for milling. And the smaller the stock is in two directions, the cheaper it will be. We're now going to move into DFM for turning.